Hello. All right, so there's double, triple, quadruple of me there. So let's get this video started. All right, so I'm gonna try to make a quick little video here for Born Haber so that you guys can do some of this stuff over the weekend and then we can finish this up next week. This is 2G, okay? This is 2G, it's all there. In fact, the interactivity we did in class was this one right here. So you can check that out. It's got the definitions and stuff in there. And then when you scroll down here, it's got a nice little video and then a sample one and then the definitions down here as well, so you can piece it all together. All right, so I'm gonna go try and go kind of fast because there's a lot here. There's a lot of stuff. Let me slideshow this thing. Yep, that should work. Okay, great. All right, so here is a Born-Haber cycle right here. Bam, it looks kind of messy and it looks kind of complicated, but it's not that bad. First big thing is you got to understand exactly what it is. So this is all of the energies for all of the steps in the formation of an ionic compound. There's a bunch of enthalpy cycles. You only have to know Born-Haber, which is formation of an ionic compound. So here's formation reaction of an ionic compound. Super simple, one step. Okay? However, you can take this one step and break it up into its multiple steps. Here they are. Bam. So the way that this works is to find this value right here, that one right there, that enthalpy of formation, it's going to be the sum of all of these and then minus all of these. This is like a big Hess's law. It's like a massive Hess's law. So I could find this value right here, enthalpy of formation, by taking 148 plus 242. We're going to talk about what all these are in just a second. Plus 738 plus 1451. That's all the endothermic steps. All of these steps are endothermic. And then the exothermic steps, which are these. So then we would have to do minus 2 times 349. We'll talk about that in just a second. And then minus 2540. You add all of this up and bam, you get this. Okay, so it's just like a big old Hess's law. Right? So let's talk a little bit more about stuff. So which ones do you have to know this for? They're going to ask you Born-Habers for any metal. It's an ionic compound, so it's going to be a metal plus a non-metal. Any metal from group 1 or group 2. In other words, ones that have a positive 1 or a positive 2 charge, like sodium, which ends up having a positive 1. Sodium, which has a positive 1. Or magnesium, which has a positive 2. Should have written these as charges, 1 plus, 1 plus, or 2 plus. And any non-metal that has either a 1 minus or a 2 minus charge, like chlorine, which is 1 minus, or oxygen, which is 2 minus. There's all the possible combinations they could give you. Maybe not sodium, it could be lithium, potassium. Maybe not magnesium, could be sulfur, whatever, of the oxygen or sulfur. All right, let's keep going. All right, so each of these has its own enthalpy of formation. They're all different. So just like that first slide that we looked at where we added them all up to give the enthalpy of formation of MgCl2, they each have their own value. We would have found the one for MgCl2 on that one and it would give negative 642. But they're all different. So there's no standard answer there. It's unique for every compound. Okay, so the example that we just did, the one above said 640 something, this says 659, and that's just because the numbers are slightly different. But this is what we already saw on the first slide, where how would we get this enthalpy of formation right here? We would take this 148 plus this 242 plus this and subtract that. So kind of did that already on the first slide, so I'm going to skip that past this one. All right, now that you know how to put that together, you have to know what each of those steps are. So here on this previous one, there's 1 step, 2, 3, 4, 5. There happen to be 5 steps in this Born-Haber cycle. But sometimes there's 4, sometimes there's 6 steps. But they can all be broken up into these main 5 steps right here. And you have to know them. So you can take these definitions. You can come through if you want. You can take these. This is a general little description of what the steps are. These are the ones that are definitions on the activity that we did. But here's the basic idea. Step one, you got to turn that metal into a gas. So atomization, sublimation, vaporization of the metal. That's going to be step one. That's this step right here. Magnesium solid into magnesium gas. This step right here, they've labeled it atomization. They could have easily labeled it vaporization or sublimation, either way. I'm going quickly. You can always pause this if you need to. The second step is breaking the non-metal. So we dealt with the metal already. We're going to break the non-metal. Remember, it's diatomic. It's diatomic. So the only way to get that thing into individual atoms is then to break that bond. So you'll notice here, we went from Cl2, which is a chlorine bonded to a chlorine, to 2 Cls, which are 2 separate Cls. And that's what we want. We want individual atoms. That's why it's called atomization, and that's why we turned it into a gas, the metal, and then broke that bond. This is bond enthalpy. Okay? Let's keep going with the next one. Next step. Now you got to turn that metal into a cation. Otherwise, they're not going to attract in an ionic compound. So we've turned the metal into a gas. Now we've got to turn it into a cation. And that might be 2 steps, because it might be first ionization energy, which turns it into a 1+ charge. Or maybe you have to ionize again to turn it into a 2+ charge, like a magnesium. And I'll show you that in just a second. So this is how they can have more than 4 steps or 5 steps. Could be step 1, step 2, and then this one could have 2 steps. Okay. All right, all of these steps right here are endothermic. I'll put it here because I don't think that's going to be able to, if I put it over here, you're going to see it. These steps are endothermic. These steps are exothermic. So starting here is where the graph starts to go down. So you notice atomization, bond enthalpy, first ionization energy, second ionization energy. We had to turn magnesium into magnesium +1, then turn it into magnesium +2. It's 2 different energies. Okay? So they put them together into one, and now we have magnesium 2+ and the 2 electrons that it lost. So that's that step. From that point forward, it becomes exothermic, and energy is released. Exothermic. Each of these chlorines is the same one we talked about in class. Each chlorine picks up 2 electrons, so this is why it's 2 times. Notice that there's a 2 here. So you're going to have to multiply by 2. Always go based on the coefficient. Okay? And then the last step. Now that you've made the cation, and now that you've made the anion, then they're going to come together. And they're going to make the ionic compound. And that's called lattice enthalpy. That's called lattice enthalpy. And that is this step right here. Lattice enthalpy. And this one can be a little bit tricky. We mentioned it in class. But by definition, lattice enthalpy is always positive. Because it's the energy needed to separate the crystal lattice into ions. But in the Born-Haber, it's negative. So sometimes they'll draw it positive so they can label it as lattice enthalpy. But you can see that to start here and end here, you've got to go up and come down. So we would do the math with this number as negative. This would be 148 plus 242 plus 738 plus 1451 minus 2 times 349 minus 2540. Okay? Okay, the activity we did in class had all the definitions. So here they are. You can get them from the site as well. I'm not going to go through them right now because you can jot them down. You kind of need to know them. Usually they don't ask you to state what it is, but maybe it's a multiple choice, or maybe they ask you to describe what it is. So I would have an idea of what each of them are. You don't need to memorize them word for word. The thing here is that where do you get these numbers? So some of these numbers are in the data booklet and some of them are not. And I'll talk about that in just a second. Okay, tricks. Tricks. Why do these problems get tricky? Well, because there's a lot of steps and you have to be careful of whether you need a first ionization energy or a second, whether you need a first electron affinity or a second electron affinity. So you've got to be careful with that. And then that means you got to be careful with quantities. How can you figure that out? Well, look at your charges. Na is 1 plus. So you only need to ionize once. Chlorine is 1 minus. So you only need to do 1 electron affinity. This ionization is the Na losing an electron to become Na plus. And this electron affinity is the chlorine picking up an electron to become chlorine negative. Remember, we want the charges so that they'll attract. Plus 1, 1 ionization energy. Minus 1, 1 electron affinity. 1 plus and 2 minus, which means you're going to need Na is going to have to do 1 ionization, but each oxygen is going to have to get electron affinity and gain a second electron. So you're going to need 2 values for this one, and so forth. Magnesium 2 plus would need first and second, and then chlorine 1 minus would just need first. And then Ca2 plus and O2 minus is the one with the most steps. Okay, you can pause and think about that for a second if you want. Now, 4 quick examples. 4 quick examples. We could spend like 10 minutes on each example, but I'm not going to do that. Here's the first example, MgCl2. Actually, this is the one we've already looked at. So I'm going to skip over this one. Bam, let's go to the next one. CaO. All right, so this is 2 plus 2 minus. So this is actually the most complicated one. This is the one with the most steps. We're going to have to take calcium and turn it into calcium plus, and then turn it into calcium 2 plus. So that's first ionization and second ionization. And we're going to see that here. Calcium, ionization energy 1 and 2. You get those numbers from the data booklet. They've already added them together. Did they add them together? Yep, they've added them together to put it here. So I don't know what they are individually, but you can get those from the data booklet. And because it's oxygen, you're going to have to do oxygen into oxygen 1 minus, and then oxygen 2 minus. So you have to do first Ea and second Ea. This one's weird because first Ea is exothermic and second Ea is endothermic. That's okay, you get that straight from the data booklet and just use what it is. We could have combined these into one like they did and just had one step going up. All right, everything else is the same. Sublimation, atomization. This one is bond enthalpy. They called it atomization, but this is bond enthalpy. It's the same thing. It's the same thing. And this would be 1/2 of the bond enthalpy because we only need 1 mole of oxygens, not 2. And if you break one mole of bonds, you're going to get 2. So how would we get this enthalpy right here? This would be equal to 178 plus 249 plus 1735 minus 141 plus 753 minus 3401. Whatever all of that gives is here. The only catch being this. We only need 1 oxygen and it comes in pairs, right? So you need 1/2 of the bond enthalpy for oxygen. But the balance reaction gives it to you. 2 more quick ones and then we're done. Next one, Na2O. Na2O, it's going to be again the same. Atomization of the Na, solid to gas. Bond enthalpy of the oxygen. You got to take the bond enthalpy of the oxygen, divide by 2. That gives you this number. And now Na. There are 2 Nas. So we have 2 times the atomization energy. That's already calculated here. And this is 2 times the ionization energy. That's why this number is so big. Coefficient right there. The oxygen has to have a 2 minus charge. So you got to go O1 minus and O2 minus. So you're going to have to do twice 2 electron affinities. Electron affinity 1 and electron affinity 2. There's 1 and there's 2. Okay. These get more comfortable with more practice. And the last example, NaCl. And Na is just plus 1 and Cl is just 1 minus. Should say 1 plus and 1 minus. So we only have to ionize once and electron affinity once. So once again, this one, sublimation. Actually, I don't like this one very much because it's got the arrows here like this. I should have maybe not picked this one. I don't like this graph very well. But the structure is the same. Sublimation is here. Bond enthalpy is here. Notice that you're going to need half of the bond enthalpy. And then ionization is here. You would never ever draw it like this, where they've got the reaction written here like this. This arrow is this arrow. Actually, I don't like the way they've drawn this one. I should have paid more attention to this diagram. All right, hopefully that was helpful. See you guys. Let me see how I can stop this photo booth now.